So while they're coming up, I need to apologize because I didn't introduce you properly. I missed the slide somewhere. So Iyad has been educated by Stanford University. He has project management and risk and decision-making degrees. He's also author of ISO 95 best practice books, number 2 and 3. Co-author of the best practice books. I think that's important because we need to update our views on operations management in this new digital area. So I'd like to mention that. Maybe let's continue with presentations. Sastry, can you say a few words about yourself?
Sure. Hi everyone. This is Sastry.
Maybe use the mic.
My voice has kind of gone a little bit sick here. Hopefully you can hear me. This is Sastry Malade, CTO of Foghorn. We're a value-based edge computing startup. Well, we've been around for 4 years. I personally myself been in the industry for almost 3 decades, working at big companies, small companies, startups. And we're seeing a lot of traction, especially trends these days from moving all of the local data processing, as in fact, Mr. Iyad explained in his presentation, moving all the analytics to the local in IoT environments.
And Adam?
Yeah. Good afternoon. I'm Adam Juchter. I'm probably the least important and knowledgeable person on this panel. I'm with Microsoft. I represent our Azure IoT solution. I actually cover the Southeast, but have been in this role for 4 years. One of the original 4 people that started with our IoT field organization. Machine learning, AI in general, touches IoT. IoT touches AI. So I've worked with Hari a few times. I actually was going to be here with my customer, Gary Cantrell from Jabil, so I can speak a little bit about what the work they're doing as well, leveraging machine learning, but I'm going to let the experts really handle most of the questions.
Okay, wonderful. Thank you so much. Do we have a mic ready for the questions from the audience? Mike Dudzik. Oh, there is another question there. Sorry, Mike.
Hi, good afternoon. Doug Stuckel from Air Liquide. Hari, for your presentation that you gave after the optimization, I was curious if the model that you developed took into account the acceleration for preventative maintenance that might need to occur on the equipment since the production rates increased dramatically.
Good question. Actually, we take into concept, so that's where the retraining of the models come in. If you had drastically changed anything in the equipment, whether it is preventative maintenance or which includes replacement of parts or things like that, then you retrain the model with the new set of fixed parameters as well as new set of data streams. So it is. There are algorithms where, like he was talking about, reinforcement learning algorithms. There are algorithms you can apply where you don't want to take that risk in an operation like this, where you're letting it learn by itself.
That's a very interesting question, Doug. In this case, we have 1% more throughput. So in terms of additional maintenance requirements, that's probably limited. However, could you also include maintenance requirements in the model? Yes. Could you optimize the operations in order to minimize breakdowns?
Yeah, so I didn't mention that in addition to throughput, energy consumption is another thing we look at. So it's not like in constraint in linear programming or mixed integer programming or nonlinear optimization, you would put a constraint, you put an objective function and try to maximize. Here, in the machine learning models, you can have multiple objectives depending on what model you choose, and then the model optimizes to those objectives.
Thank you so much. There was a question by Mike Dudzik here, and then there is a question from Exxon.
It's touching on same, Hari, just touching on the same, when you talk about the model maintenance there, do you have in your toolkit some kind of visualization or something that says your model is starting to drift and you need retuning, or is it something you do on an ongoing basis there? Typically these kind of things, there's always wear and tear, and you're maybe moving into different operating regions there,
Yeah,
such
so-
that the model needs to be
Yeah.
redone.
Yeah, so they're very well established. I would say well established. I would say very well known approaches to know model drifts. Like think of it as you have statistical distributions of these variables, right? So if the distribution drastically changes, whether it's a mean shift or the change in any of the statistical parameters, you can detect through algorithms. So we
Standard
do.
deviation.
Yeah,
that
so
kind
we
of thing.
do periodically run whether the model has drifted, and then indicate that, then you have to retrain the model.
If I understand well, the machine learning or the neural nets or AI provides basically a simulation scenario. It does not do optimization. Is that correct? That's what the literature says.
Yeah.
So basically, you don't optimize like real-time optimization where you invert the model. In AI, you just do simulation. How you get the optimized performance?
Yeah, good question. And theoretically, you're right. It's not a mathematical optimization, but if you look at the example I gave, your idea is throughput optimization, which is the maximum throughput you can send through considering a certain set of constraints. And
What if studies to run to mimic the optimization? You give different input until you find the best throughput, and that's the answer.
No. You are dynamically changing your thresholds to conditions you are seeing, right? In a standard optimization, essentially you'll have to rerun an optimization several times. So what the machine learning allows you to do is kind of adjust to the changing parameters. Yeah, go ahead.
Yeah, so in general, I think your observation is right. Machine learning by itself is not necessarily going to optimize or fix things, right? Machine learning helps you identify, to predict based on historical information, historical data, in creating a model to say, look, when these such and such conditions occur, this is the output that's going to be, right? Now, based on the output the machine learning algorithm is going to tell you, you can further then use closed loop control actions to either stop the process, change the parameters, and then further benefit from the optimization. So the key point here I'm trying to make here is that machine learning by itself doesn't fix things, but it helps you to identify where the problems are, predict them, that you can use that as an input to use the closed control to take actions to optimize the process.
In that sense, it's similar to the real-time optimization because it provides you the optimal conditions, and then the APC does the job.
That's
Is that
the
correct?
Yeah, that's exactly what we would.
If I can summarize whatever you said, you're trying to find the best performance in the history, and that's your optimum, that's the optimum.
Right, you're going to take both good, yes, that is correct.
The scenarios
Right.
changing, that performance is not optimal.
No,
I like
I understand.
real-time optimization that you gotta be optimized.
Right.
I don't want to continue that. I have another question for people that we just hear only the good things about machine learning and the literature also indicates very easily that the robustness properties of machine learning are extremely poor. So in other words, if you have 1 million parameters in the nodes, 3 parameters to change, instead of recognizing an elephant, you might recognize a rocket. Is that correct? How you deal with the robustness of the model that you have, like if the input is, you have some disturbances and so on, usually the neural nets will take you off the cliff. Is that your experience?
It's not quite exactly right. So the traditional computer vision models do suffer from that problem that you're referring to. But in the neural nets computer vision-based models that Mr. Yadav explained, for example, right? Especially in a supervised learning model, when you take all these million parameters or X number of parameters and then construct a model scanning pixel by pixel and try to come up with this, look, this is this image. and you try to compare it with what was the real image, and if it's a false positive, right, then you take that as a inaccurate statement. So when you do a lot of this over a period of time and observe how accurately was the model predicting it, and if the model was accurate, then you take that as a labeled good model. This does not mean, actually there was another comment that was made earlier, I wanted to clarify on that. This does not mean when you develop a model once that the model is going to stick there forever and is good forever. It is not. Typically what happens is over time, just like there is behavior in human beings, behavior in machines do behave differently too. Because of machine behavior, data behavior changes, calibration issues, there's going to be data drifts. Those data drifts cause the model drifts as well. What it means is that once upon a time, a model that was developed and deployed, which used to accurately predict what's actually coming out right, may no longer accurately predict at the same time. It's the same model. Why? Because the behavior of the data is changing, data is drifting. To account for that, and this is where I think Hari mentioned earlier as well, there are a number of techniques. You can use what is called an F1 score, which based on precision and recalls to compute to say, is my accuracy of the model drifting? And we have, for example, tools that allow you to detect automatically if there is degradation in the model definition, model output. And as soon as you do that, then you start retraining, revising your model based on the current data that's coming in. This is where what we call the closed loop ML or the machine AI, artificial intelligence, come into picture. In other words, it's not a one-time deal. You take your computer vision model, do all of these parameters, check with all those false positives, deploy the model, continue to monitor for data drifts, and then revise the model as necessary. That's truly when you're going to actually benefit from all of these different techniques.
That's actually true for model predictive control as well. You also need to retrain the model. Is there a question there? Yes, please.
Yeah. Hi, my name is Gopi Balakrishnan with Tata Consultancy. I want to use Hari's presentation where you said the throughput was improved by 1% as an example, and open this question to anybody in the panel, including yourself, Hari. Typically, when you are dealing with your end customer, selling them machine learning or predictions for improving their yields and what have you, you're kind of trying to explain something to a set of people who are not yet at the same level of understanding and comprehension of the benefits. So, and then from an operational standpoint, there are a lot of other things going on, like in a gold mine, that you cannot have a controlled experiment. So how do you, impress upon the customer or the end user, the sponsor of that project, of the benefits, or claim that 1% was because of the machine learning and not because of some other factor that happened there? Just some perspective on that, please.
Yeah, a couple of things there. First, you have to have a pretty committed party on the other side, right? Who's really interested in. They have been looking at different ways to improve throughput. All different techniques, process improvements, equipment improvements, control systems. They've done everything. So you first have to have a committed customer. And then the second thing is, on our team, one of the things we worked very closely with them is people who understand the domain really well. It's very hard to go in and say, okay, there's a black box algorithm that's going to solve. And I come from supply chain optimization background from the late 80s, early 90s, where we built supply chain optimization system, which we ran into the same challenges, right? You have a mixed integer program which outputs results and says, okay, this is what you need to manufacture today. Why? You need to have the explanatory part. So you have to have a combination of domain experts and the data scientists or machine learning experts to be able to kind of educate, implement, and then sell solutions like this. That's our experience so far.
I can
you
actually
so much.
answer one question. Finally.
Go ahead.
So when you're thinking, to add to what Hari said, having that domain experience, that domain knowledge, when you go in and you're talking to the customer and you have that expert in that area, they're going to have an idea. They're going to say, we think that this might be causing some issues or this might be causing some issues. One of the great benefits of leveraging the cloud, leveraging these kinds of new technologies is you can iterate so quickly, right? That you can, at a somewhat limited cost, try and find a solution. The machine learning question that came up before, that was what was going on in my mind, is that you try these models, it doesn't work or it doesn't show a high correlation. You try another one, it doesn't work, high correlation. You try another one. One of the great
Experiments are cheap, you're
yeah,
saying.
right. So I often use a term called think big, start small, and go fast, which, right, think really big. What's this big idea? If we have this idea of increasing throughput, that's going to generate some savings or some improvements. Let's start small. So let's look at one area of it, maybe one of those mills, right, and start with that and see if we see some improvements there. And then go fast, scale it. Once you find something that works, scale it out.
That's
Yeah, understood.
a very good point. Well, the other addition to that is, at least in the last couple of years, where or 3 years we have been involved, it is we never come in and claim that it is the results a priori, or it's never a controlled system. It is an advisory. So you start off as an advisory and build enough confidence, right? I feel that's how you get adoption of these systems.
Yeah, it keeps the operator involved, and that brings us to Iyad, I think, who made comments about that, which I found very interesting. You said that if you have the operator making the decisions, they get the ownership. If you do that by a center of excellence and you send the results back, then they lose interest, so to speak. That part I understand. And then you say that reduces the total cost of ownership. Can you explain that a little bit?
Mainly, the total cost of ownership is associated with the level of utilization of the technology.
Okay.
If they don't feel the sense of ownership of that technology, they will just ignore it. So you will not realize actually the benefit.
Yeah.
And I agree with the gentleman that we are not at the stage that we can allow the machine learning or the AI to close the loop and to
Right.
go immediately and change the set points, because until now we didn't reach to that level. Maybe in the future where we have more trust on the model, but until now it is an open loop. So as I mentioned, is that they will give you the advisory of what need to be done, and based on their experience and then their analysis, they will decide to what are the best control measures that they need to apply.
Thank you very much. Before we go to the question there in the corner, I have another question for you. I think you said that you used the image processing as well as more classical process control variables and analysis of process control variables, such as the valves.
Yes.
So what made you choose for one solution or another? Did you compare the two? Is one more effective?
Yeah, it's when we use the CNN, it's good for the image processing or the unstructured data,
Right.
and the random forest was good for the time series kind of data.
I understand, but now in terms of performance in detecting a flare, what is your preference and why? Why would you use traditional process control data?
The corporate flare monitoring system that we have implemented is another innovative way. It's based on the opening of the valve and the amount of the material that we are flaring. It will detect and will give you the analysis based on whether you are meeting the regulatory compliance measures or not. So to complement this, we are using the non-traditional, which make more use of the data that we don't usually use in our analysis model, which is the image and so it's a complementing, it's not replacing.
It's complementary.
Yes.
All right. Thank you so much. Question.
Thank you guys for coming to talk. Valentin, you actually just kind of touched on what I was going to ask about. So maybe just to dive a little bit further in that use case, I'm curious to know, with all these different techniques that are running on the flare tip right now, what ultimately is the user looking at when they see these alerts? Are they looking at what's coming out of the machine learning anomaly detection and the image detection and all of these different algorithms at once, and then they make a determination to close the loop? Or are you just surfacing one of those insights to the user now?
I think what are the components that you are looking at?
So, okay, so we started with saying first we're running anomaly detection right on the valves.
Yeah.
And then we started doing image detection.
Yes.
And I'm just curious, are all these things still running on the flare tips right now? And you have somebody that's looking at all these different algorithms and alerts to make a determination on whether or not, I need to do something to close the loop here? Or are they looking at just one of those algorithms and
No,
anomaly detection is just firing off a bunch?
No, it's all actually. It's to complement our company dedication on reducing the footprint of the hydrocarbon. So all of these dashboards that you saw here in the example are monitored on the CEO level. And we are putting a very important, dedication to reduce the hydrocarbon footprint. So whatever we are investing, actually this example, it didn't cost us much, but the total investment is 1.2 billion. So we are doing whatever it takes to reduce the footprint of the hydrocarbon within our plants.
Okay, so use them all in parallel.
Yes.
Now, next question could maybe be, what do you do next? What is the learnings? Do you feed that back into reliability programs? How can you work on avoiding these issues? Detecting is one, but avoiding is maybe the next one.
That's exactly what we are doing. We are doing the classification of the type of things that is causing flaring, whether it's the problem with the valves itself, or it's a mishap of the operator, or it's an issue with the flare head. So based on that, we do the corrective action that is needed to minimize and eliminate the flares.
Okay, wonderful. Thanks for the question. Anyone else? We're through the questions. Okay, there's one. Mike.
Just for Ayad, when you added the edge computing with your cloud, your cloud went to like a manager and then orchestration to the edge. Can you explain a little bit more about what all that means? That sounds very interesting. You've changed what the cloud is now doing with the edge. Can you explain how that works?
It's mainly that instead of waiting or sending the control points or control measures from the cloud, now they are just verifying if whatever we are doing by the operator is okay, and they do some orchestrations that they set a priority or what should be done by the operators. And maybe
That's great. If I may comment on that, that's exactly right. What previously, all of that information that needed to be sent to the cloud, where you go build your models, set your priorities, change your parameters and everything else, that's all done locally there at the edge. But the prioritization or what parameters are important, who needs to do what itself can be controlled and orchestrated, deployment and everything else to the cloud.
Thank you.
Are you sending all the data to the cloud at some point in the day to do your modeling later?
So typically, that's actually a good question. Typically, for modeling purposes, you may send some historical data to the cloud or offline box where you create a model. But once the model is done and you deploy the model, you don't need to send all of the raw data to the cloud, which is effectively is going to cost you a lot more, plus cost a lot of bandwidth. But instead, you would only send the results or the information that they need to know based on which they can act on.
We're through. So I'll ask a last wrap-up question. What are the opportunities we see out there for the next few years? The greatest opportunities that you can identify?
So from my point of view, the opportunity is to allow the true automation of this. So the machine learning to start recognizing the data drift, calculating the appropriate models, and starting to adjust itself automatically. I think that's where we're going to see another leap forward. We have a lot of data. There's so much data out there. That's not the problem. The problem is making sense of the data. So being able to allow the machine learning algorithms to actually adjust themselves, but then also the visualization. I know Iyad mentioned the visualization tool that they're using, the dashboards, and how that's got visibility all the way up to the CEO. That ability to consume that data and democratize those insights is another area where I think we're just going to continue to see better things on the phone, et cetera, right, where we're able to monitor things and take action in near real time.
Actionable information at lower implementation cost.
Right. What I would say is we see tremendous traction and progress in digital transformation. I know a lot of companies have begun their journey on it, but we're barely still, we feel that we're scratching the surface, right? And especially in the industrial and commercial environments where it is simply not practical to send all of the data or the information to a remote location, to have somebody process it, take some decisions, send the information back there. Where we see, but what are some of the challenges of just directly moving the compute to the edge environment itself? As Mr. Yed talked about, many times it's accessing the data. How do you access the data? There are some of them are traditional old data systems as well. How do you get access to that? There is no compute environment. How do you do all of this in a small constrained compute environment as well? I think this is the area where edge computing, digital transformation, do local processing and eventually get to the automation. People are not going to on day one, as many of you have commented out, do closed loop control in the sense that they want to first get comfortable that what's being detected is in fact the right thing to do and have an operator manually take a look at it to see if that's the right decision to make. Once they get comfortable, then get into the closed loop. I mean, that's step number 2. I think there's still a lot of work that needs to go for step number 1, where adoption of this across all of these different industries, I think is the best thing for the next couple of years, I see.
I think there are a few pockets, right? There is the constrained neural networks. I forget exactly what the name of the invented by AspenTech that seems to be applicable to closed loop control.
There are. So, I mean,
There are
we
a
have,
few
for
pockets.
example, I mean, we have Foghorn has implemented a closed loop control as well. A number of other solutions exist. What I'm trying to say is that deploying this in production environment where without the operator's involvement, automatically fixing it, operators are not quite comfortable yet, right? Technical solutions do exist.
That's a good point. Even if you could do it closed loop, I think it's important to create that visual so that the operator understands what's going on.
Exactly.
And that is one of the main reasons that operators switch off the APC applications, because they don't understand what it's doing.
Right.
So that's a great result from this session. Iyad.
The opportunity that I see is that we have zettabytes of data generated by each of these assets. And as we saw in the presentation, is that a lot of this information or details of this information get lost in the way before making the decision. So by realizing the benefit of this data, converting the data into information, knowledge, and insight to understand what are the root causes, and identify what are the corrective action that could we make, will help us in reaching the optimization, and eventually maybe we'll go with the closed loop once we reach there.
Thank you.
Yeah, I agree with everything that was mentioned so far. The only addition is context is extremely critical when you do any machine learning based. When I say context, today context resides in multiple systems in the enterprise, which means you have an EAM system, which let's take asset performance. You have an enterprise asset management system. You have a MES system if you're in the manufacturing. You have historians where you're collecting time series data, etc. The context of this exists in multiple systems. Now, the approach a lot of people have been taking is, okay, we need a big data project first to bring all this together before you can start any of these machine learning approaches. That's kind of is slowing down the innovation in this space. Our recommendation to a lot of our customers is, I think Adam, you mentioned, is like you can start very small and get some serious benefits if you define the problem well. You don't have to take on this huge megalith of a big data project to make sure all the data comes into one, what you call as a data lake, or we joke about it as data swamp, and then try and figure out what is needed. You could do it piecemeal, get some significant value. From the future perspective, machine learning and what has made machine learning possible right now is it's not like Valgren presented. It started in the 50s, late 50s, early 60s. Herbert Simon, people, I went to CMU. You can see pictures out there of folks who have been doing artificial intelligence in 60s. And what has made it easier is the compute and storage. The cost of compute and storage the distributed computing, like Foghorn mentions about edge computing, being able to scale very easily, the tools that are there from a software deployment perspective, automation perspective. We talked about containers and virtual machines. So all of that makes it much more easier to handle large volumes of data, run a learning model, and that's what is different right now. So I expect this to accelerate. I think there's some teething problems. And there's a lot of change management, cultural issues as well.
Yeah.
But there's one on the other side. There is an aging population, aging of folks, subject matter experts. So that'll make it really a driver for accelerating.
For doing more. Yes. Yes.
Faster. Yeah.
Thank you very much. It was a privilege to have you and have this highly involved and interesting discussion. Thank you to the public to coming so numerous and staying late with us. Thank you so much. Don't forget to rate the session, please. And then I wish you a nice evening. Thanks.